Hello, my name is Bob D. Hilster, and I am your particle model guru. Today I'm going to talk about the speed of the G2. One of David's viewers asked this question and wants to know how we can say what that speed is. However, if you are new to the particle model, haven't viewed very many of my videos, I suggest that you watch these two in particular, the TPM, the particle model overview, and the levels of the universe. You watch both of these, they're not long, you'll get a pretty good idea of what we're trying to say the particle model is. Well, Dave and I have said in our videos that the speed of the G2 particle is c squared. And we're being asked, well, how can we say that? So let's take a closer look at the levels of the universe. There's level 1. The particle model has two particles in the level 1. There's the N1, which replaces the neutron and the proton, and there's the G1 orbital, which replaces the electron, which orbits the atom at level 1. With these two particles, all the atoms in the periodic table can be built. For example, one N1 with one G1 orbital makes a hydrogen atom, and you can build all the rest of them from there. Level 2 also has two particles. They are called the N2 and the G2 orbital. And these two particles can make atoms, specifically subatomic atoms. Now, I don't know how many there are, but I'm suggesting there's at least one. But it's more likely that if there's one, there's more. But mainstream science never mentions subatomic atoms, only subatomic particles. And I'll go into the reason why the particle model says it this way. Now, the source of the G1 and G2 particles come from the stars. G1s come from the stars as streams of light. Now, we've said in other videos, showed you what light is in the particle model, and it's a stream of G1 particles with a repetitive pattern. And of course, the sun also can release individual random G1 particles. And this combination is called the G1 particle field. G2s are also released from the stars as streams of G2 light. That's an idea I just threw in there. Could there be light at level 2? Haven't gone there yet. But they also are released as individual random G2 particles, and this combination is called the G2 particle field. And this is the level 1 stream of light. These are G2 particles. This is a stream of G2 particles here. There's a whole bunch of them here, very few here, and another bunch here, all moving at speed c in some direction. And it's this bunch here and this bunch here define the wavelength of the light. This pattern was developed by Dave mathematically based on a sine wave, but they could be any pattern at all. It could be any. It could be a pulse, could be a triangular wave, could be anything. All depends on the distribution of that, and for light it has to be repetitive. This is the particle model's view of what light is. Now, when I first discovered or came up with the idea that that's what light was, I then applied it to refraction. And I grabbed this figure, and I'm looking at this laser light, and I'm assuming this is a stream of G1 particles here. It hits the prism and bends, and it comes out of the prism and bends again. And I ask myself the question, is there a force, or more accurately, what would the force have to look like if it were to cause light to bend? And I drew this arrow. I said, well, that makes sense. That's what the force should be. Then I noticed this one down here, and I said, well, wait a minute, it bends here also, so let me go ahead and draw that one. As soon as I drew that, something hit me. I had been drawing arrows like this around objects when I was doing gravity for 10 years. I did this all the time. And for example, if I were to draw the force of gravity, Newtonian gravity around the Earth, I would draw arrows like that. After testing the prism, and I realized that all of the forces that could bend the light would be perpendicular to the surface, I drew this picture. Now the question I'm asking is this is Newtonian gravity. Is this Newtonian gravity? And my answer was no, because this gravity tends to move objects like apples and moons and galaxies. This is not moving that. This is, when you bend the light, you're moving light. You're moving what the particle model is now calling the G1 particle, or you might call the photon. So it has to be different. And so I said, well, maybe there's a gravity 1 and a gravity 2. To make it a long story short, as time went on, gravity 1 became G1, gravity 2 became G2. And when I worked on gravity, my gravity was always based on the graviton or a gravity particle. So the G1 became the name for the gravity particle. G2, well, we don't have a name. There is no, subatomic atoms don't exist in mainstream, so I don't know what to call this other than, for the moment, call it a G2 particle. If this is a particle, then this is a particle, and that's where the origin of the G2 particle came from when I applied the particle model for light to the prism. Gravity 1, the G1 particle, not only keeps the Earth together, it holds air and water and all things together on the Earth. It also keeps the moon orbiting around the moon orbiting around the Earth. G2 gravity holds the nucleus together, and I've said before that it's the nuclear binding force. G2 gravity, nuclear binding force. It also keeps the G1, which is the electron in your terms, in orbit around the nucleus, around the N1. That's G2 gravity. And that's the G2 particle that's keeping that going around. So ultimately, now we get back to the question, how fast is a G2? Well, I don't know. But I can say some things about it, or what it could be. But if the G2 can bend light, as in the prism example, can keep electrons in orbit, or G1s in orbit around the nucleus, if it can keep magnetic fields in orbit around and through the magnet, the magnetic field, according to the particle models, made from high-intensity streams of G1 particles with no repetitive pattern, and there are more examples. The G2 can do all that, then the speed of the G2 must be faster than the speed of light. Yeah. Particle models suggest that there is a particle, we called it the G2, and it moves faster than the speed of light. It couldn't do this. It couldn't catch up with and push the G1. It has to be faster. This was my first estimate. Yes, this is a seat of the pants estimate based on my own statement here. The speed of the G2 is faster than the speed of the G1. by the ratio of the speed of the G1 to the speed of level 1 atoms, which are basically, I'm talking about Earth, Moon, asteroids, and so on. So I'm saying that since the G2 comes from a subatomic particle, atom, and then the G1 is part of a regular atom, the ratio of those speeds is the same as the ratio of speed of the G1 to the Earth and Moon. And if you've looked at it, you'll see that the Earth and Moon and all the other objects, they don't move very fast. They move pretty slow. But I can change this to an equation. The speed of the G2 is to the speed of the G1, as the speed of the G1 is to the speed of the Earth. Or I can change the speed of the G1 to c, since the G1 is moving at c, and then multiply through by c, and I get the speed of the G2 is c squared over the speed of the Earth. So you can see where the idea of c squared comes into play. Now this isn't c squared. This is less than c squared. The speed is less than, because it's divided by, and you can pick any arbitrary number, so it doesn't absolutely define the precise speed, but it gives you a notion that it is some ratio of, some fraction of, or some multiple of c squared. Okay, the last thing I'm going to talk about in terms of speed is the speed of level 1 objects are subject to G1 drag. As the Earth and the Moon go through the G1 particle field, which I talked about earlier, it is my contention that the speed of the Earth and Moon are being slowed down by G1 drag. In other words, as it moves through this field, the head-on collisions are stronger than the rear-end collisions, being pushed back more than it's being pushed forward. It's called drag. But since the speed of the G1 is so high, it's c, then the drag is small. It's there. Scientifically, I have to say it's there. And yes, it's contention that they are being slowed down, but the drag is small. The speed of the G1 is subject to G2 drag. Now this was the motion of the Earth or the Moon. Now I'm talking about the motion of the speed of the G1, and it's subject to G2 drag. If the speed of the G2 is too low, then the G1 light will slow down too much, and as it travels through space. And although it's my personal opinion, it does slow down. If it's going to maintain its speed over some interval of time, long time, then the speed of the G2 must be high, and in a sense it must be higher than c squared over the speed of the Earth. Probably much higher than that. So what is the speed of the G2? I still don't know. It's at least c squared over the speed of the Earth, or whatever you want to put here. But it probably is much higher, so that drag is not a problem. But to keep it simple, I tend to say that the speed of the G2 is c squared, or even faster, or I might say it's c squared at or about c squared, or I might say it's nearly c squared. Can't really pin it down. It becomes a simple phrase to say, but the fact is I don't know what the speed of the G2 particle is. All I know, one of the things I do know, it must be faster than the speed of light, and very much faster than the speed of c light. And the term c squared at least gives the impression of a very high speed. So if you're new to the TPN, let me remind you again, you can get an overview of a particle model by watching these two videos, TPM Overview and Levels of the Universe. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the particle model I will explain more of the particle model. Thank you for your attention.